Hello everyone and welcome. My name is Hanin Abu Zaid from the Lebanese Center for Water and Environment. I'm very happy to have you all with us today for session 2 for our cross-learning GIS school. For those joining us for the first time, LCWE is a research center that works to improve water and environmental management in Lebanon. We focus on research, capacity building, and community awareness, and we collaborate with local and international partners to support sustainable and science-based solutions. This program is special because it brings together LCWE and ESRI Lebanon. Together, we provide both scientific knowledge and technical training. By attending all sessions and completing the final assignment, you will receive a certificate from ESRI Lebanon. Thank you again for being here and for your interest in learning GIS. We hope you will enjoy today's session. Now I'm pleased to give the floor to our trainer, Mrs. Zainab Baalbaky, who will lead the session. Thank you.
Good morning, everyone. And welcome back to the second session of the GIS school, dedicated today to advanced image classification techniques using ArcGIS Pro. The session builds directly on our previous work, where we established a solid scientific foundation and a clear methodological framework of processing satellite data. We stressed a core principle: any classification model or advanced analysis built on uncorrected data is scientifically unreliable. Accordingly, we focused this previous session on converting imagery from visual representation into quantitative information that supports a scientific interpretation. By understanding remote sensing data sources, sensor spectral characteristics, and the steps of radiometric and geometric correction, image enhancement that ensure data consistency and analytical validity. We then applied spectral indices such as NDVI, which provide an essential entry point for assessing vegetation cover. Today, we will move from data preparation to decision making. We shift to the central stage of the analytical workflow, extracting especially meaningful information. The key question guiding this session is: how do we transform billions of pixels into actionable geographical knowledge that supports analysis and decision making? In other words, how do we convert spectral patterns into thematic maps that tell us where forests expand, where soil degrade, where irrigated agriculture intensifies, and how land cover evolves over time? Thus, we are not just learning algorithms, we are connecting analytically techniques to real environmental problems. We can consider, for example, a pressing national challenge. Water scarcity is undermining sustainable irrigation in the Litani River Basin. The goal of our research and applied studies is to contribute to addressing this issue by identifying the optional, identifying the optimal sites for rainwater harvesting ponds. Let us suppose that our area of concern is the lower Litani Basin. The solution will be by integrating advanced image classification with spatial modeling, enabling evidence-based decisions rather than theoretical discussions. To achieve this, we need a robust two-step workflow. The first step is about advanced classification. We must first train a highly accurate model to map the current land cover, specifically to pinpoint areas of bare soil and low vegetation that are ideal for constructions. The second step is about spatial modeling. We will then take the output of our advanced classification, which is the land cover map, and integrate it with other critical factors using a weighted overlay technique. To guide throughout this process, we will cover 4 core themes for today. This is our roadmap for transforming raw data into a final decision support tool. The first theme will be about the theoretical framework, the scientific basics of classification, spectral signatures, and the role of spatial attributes. The second theme is about advanced classification techniques, how we can move from pixel-based to object-based image analysis and deep learning models of high accuracy mapping. The third theme will be about accuracy assessment and quality assurance using advanced metrics to evaluate performance and identify model bias. Then the last theme will be about integrating classification outputs where we can apply the result in suitability modeling using a weighted overlay for water resources management and agricultural planning. By the end of today's session, you will have the methodological tools to move from pre-processing and spectral indices to interpreting, classifying, and modeling land surface process within a robust scientific framework. We can hands-on practical application, experience solving real environmental challenges through advanced classification in ArcGIS Pro, and understanding accuracy assessment and quality assurance for reliable results. Through this methodological sequence, when we talk about first correction, whether radiometric and geometric, to indices, classification, and modeling, we establish a reliable analytical framework that equips researchers and engineers with precise tools to study land vegetation or water resource within a scientifically robust spatial context. Today's session positions us for the next stage, which is about temporal analysis and dynamic modeling. We are not just learning algorithms, we are solving real-world environmental challenges with precision and scientific integrity. Before moving into the practical workflow, we first need to establish a clear understanding of what scientific classification actually means and how it functions within the remote sensing framework. Classification in remote sensing is the process of converting raw pixel reflectance value into meaningful thematic information that can be used in spatial and decision making. According to NASA, this is the most important stage that translate satellite observations into real Earth surface features such as water, and if we say bare soil, agricultural land, and forests. ESRI defines it as sorting image pixels into a predefined number of classes based on their spectral values that can produce a thematic layer that can be geographically interpreted. This step bridges the gap between what the surface looks like and what the surface actually is. It enables us to move from describing how the surface looks when we talked about bright red or dark colors to describing what the surface actually is. So we can talk, we see water, vegetation, or etc. It is what gives satellite data its value for scientific and environmental decision-making. Now that we understand what scientific classification is, let us discuss why it is essential in remote sensing and GIS analysis. Satellite imagery is a large matrix of pixels that cannot be interpreted directly for scientific analysis. We can say that classification converts this raw data into meaningful land cover categories such as always mentioned, vegetation, water, and built-up areas. This transformation enables us to perform several key tasks. The first one is about environmental and land analysis. By classifying land cover, we can identify environmentally sensitive zones, or we can detect the land degradation and bare soil expansion, and monitor water bodies or other. We can also quantifying a change of over time, like classification allows us to measure forest loss or agriculture expansion, or maybe we can measure the urban growth. Providing this constant inputs of multi-temporal comparison. The third one, classification, let us supporting environmental modeling, hydrological, ecological, and erosion models all require categorical land cover inputs, which the classification provides. We can also, by classification, we can search about agriculture and resource monitoring. We can estimate the cropland extent, assess vegetation stress, and map areas under cultivation pressure. From a scientific perspective, always research need measurable, comparable, and repeatable information, not only just visual impressions. So classification answers 4 core spatial questions. Where is the phenomenon? How much area does it occupy? And how is it distributed always, and also how is it changing over time? Classification converts spectral data into structured, scientifically usable categories that support rigorous spatial analysis and evidence-based decision. If we take as such example, for our instant studies, in the lower basin of the Litani, classification allows us to map bare areas and exclude the agricultural and sensitive zones and generate a reliable land cover layer that feeds directly into the suitability model of optimal rainwater harvesting ponds. Now that we have discussed why classification is important, let us look at the scientific basics of or behind it. Before applying any classification method, we need to understand the principle that makes it possible. Classification works because every land cover type on Earth interacts with sunlight differentially. As we mentioned the last session, this interaction produced spectral signatures, which we said a distinct reflectance pattern across the sensor's bands. For example, water has low reflectance, and healthy vegetation reflects strongly in the near infrared. Built-up areas have irregular high reflectance. NASA emphasizes that these differences form the foundation of all classification algorithms. Without a distinct spectral behavior, separating in classes would not be possible. The second key concept is spectral separability, which means how clearly one class can be distinguished from another. Here we can talk about high accuracy, which requires two things. The first one is about internal homogeneity within each class, and the second one is about clear separation between different classes. When classes overlap, like dense or spare vegetation, advanced classifiers, such as random forest, if we said, handle this overlap better because they model nonlinear class boundaries. Several factors influence separability, including atmosphere effects that distort reflectance, and sensor characteristics such as the number and width of bands. Thus, we can talk about seasonal phenology, especially when we are talking about vegetation, and the mixed pixels, which are common in medium resolution imagery. As analysts, always our goal is to maximize separability by choosing appropriate bands, applying corrections, and selecting the right algorithm. In summary, classification is not guessing. It is based on physics. Surfaces are distinguished because their spectral signatures are measurably different. The clearer these differences are, the more accurate the resulting land cover map will be. In this section, we broaden our understanding of how classification is performed in remote sensing. We move from a simple pixel-based approach to object-level and deep learning techniques. This structure reflects how classification has evolved over the 2 decades. When we talk about level 1, the pixel-based classification, this is the earlier and still widely used approach in remote sensing, which is the pixel-based classification. Here, each pixel is treated independently based on its spectral values. This method is efficient for multispectral imagery, such as Sentinel-2 or Landsat. By ignores a spatial context, building pixel might be misclassified, considered alone. When we move to level 2, which is object-based image analysis, OBIA segments the image into objects, groups of pixels with a similar maybe color, a shape, texture, or context. This approach integrates spectral values, shape, where maybe we can talk about rectangular or irregular areas, texture, we can distinguish between a smooth, rough, or patterned, and a contextual relationship. Maybe the relationship is adjacency or a neighborhood relation. This makes the approach very effective for high-resolution data, such as word view. ESRI emphasize OBIA in workflow where the goal always is to map buildings, road networks, or maybe we can reach the tree crowns or agricultural fields. When we reach the level 3, we can talk about deep learning classification, which is the most advanced level. It used convolutional neural networks that mimic how humans recognize objects visually. Deep learning doesn't rely only on spectral reflectance. It automatically learns spectral and spatial, textural and contextual features. This always makes it particularly powerful for building footprint extraction, or maybe we can reach crop type mapping, wetlands, or also we can map the vegetation structure. This always requires large training data sets, but offers the highest accuracy. ESRI and NASA both highlight deep learning as the most accurate method when sufficient training data is available. So always from pixels to object to learn features. These methods represent a hierarchy of precious and complexity, enabling accurate land cover mapping across diverse environments. Next, we need to understand an important distinction in classification, which are spectral and informational classes. Classification fundamentally distinguishes between two types of classes. When we talk about spectral classes, these are about clusters of pixels that have a similar reflectance behavior. They are purely mathematical grouping in spectral, or they are purely mathematically grouping, yes, in a spectral space. For example, pixels with a similar red and near infrared reflectance value form a cluster, regardless of what the land cover actually is. While when we mention the informational classes, these corresponds to real physical features, maybe about water, about forests, or about building up areas. The core task of all the studies of classification is mapping spectral classes to informational classes. It is important to note that a spectral cluster may correspond to vegetation, but it can also include mixed types. It corresponds maybe wet vegetation or dry vegetation or shrublands. Therefore, the analytic or the analyst must combine knowledge of both the spectral properties and the ecology of the study area to correctly interpret the classes. Now, let us look at the types of classification approaches. We can start with the first approach, which is unsupervised classification, which is the exploratory. Here, pixels are grouped automatically by a spectral similarity, no training data. The second approach is about supervised classification, which is the analytical approach. Here, training samples are supplied. The classifier learns each class's spectral signature, where when we reach the third approach about object-based image analysis and deep learning, these advanced models or these advanced methods combine a spectral, a spatial, and a texture feature essential with the high-resolution data. To understand how unsupervised analysis works, let us start with a simple real-world analogy. Imagine you enters a forest as a research, and as you walk through, you observe plants with different shapes, different colors, and texture, and also different forms. Even though, without knowing their scientific names, you directly begin grouping them. You can put or group broadleaf with broadleaf, thorny with thorny, and flowering with flowering. These are a phenotypic cluster created purely based on observable characteristics without any labels. This is what exact unsupervised classification does. It forms groups purely without relying on prior knowledge or training data, just like you grouped plants in the forest by their visible traits. The algorithms group pixels based on how similar their reflectance values are across different bands. Building on that, the unsupervised classification is a discovery-based approach that reveals the natural spectral structure of the landscape without prior knowledge. The algorithm knows nothing about the area of interest. It simply analyzes pixels reflectance and group pixels that behave similarly into spectral clusters. These clusters are statistical patterns, not land cover classes, so the interpretation comes later. Each algorithm is used under specific conditions. K-means is used with fixed clusters. ISO cluster is optimized for multispectral imagery, and ISO data adapts best to heterogeneous terrain or complex landscape. Once clustering is complete, the key task is assigning meaning, overlaying the clusters on the imagery and using ecological and spectral knowledge to label them as maybe vegetation, maybe soil, or built-up area. This approach is most useful when entering a new unknown or unnamed area. Ground truth is unavailable, or when we want to reveal a natural spectral grouping before defining a training sample. Its strength because it includes speed, no need for training data, and the ability to expose unexpected patterns. Its limitations are that clusters don't always match real classes, and expert interpretation is essential. As a short brief, unsupervised classification provides the initial spectral structure of the landscape, giving us a scientific starting point before producing operational land cover maps. The workflow of unsupervised classification follows a clear and structured sequence. First, the algorithm begins by initializing a set of spectral clusters. These are simply starting points based on the number of classes we specify or the internal setting of the method. Second step is each pixel is assigned to the nearest cluster center according to its spectral behavior. In this stage, the algorithm doesn't know anything about land cover. It only detects reflectance patterns. The third step is now the cluster means are recalculated, and the algorithm iterates several times. With each one, pixels may shift from one cluster to another until the groups stabilize and no significant change occur. The fourth step, which is after the clustering stabilized, our role as analysts becomes essential now. We overlay these spectral clusters on the imagery and interpret them, assigning each group to a real land cover type, vegetation, soil, or water. The fifth step, we refine the result by merging similar clustering, removing noise, and improving boundaries. Finally, we validate the output using visual checks or limited field points to ensure that the interpreted classes reflect real conditions. So, unsupervised classification reveals the natural spectral structure of the imagery, and we complete the process by interpreting and refining those groups into operational land cover dataset. Now we can move to the core technique used in most scientific remote sensing studies, which is supervised classification. Unlike the exploratory clustering, this method is analytical. It starts from what we already know about the landscape and teach the algorithm how to recognize those land cover types. To understand the concept, imagine taking a new field assistant into a forest. You show them examples of pine or maybe oak or olive trees. Once they learn these reference samples, they can classify the rest of the forest. Supervised classification works the same way. We provide example about water, forests, and the model learns their spectral signatures, then applied them across the entire image. This approach is analytical because it integrates field knowledge, expert interpretation, and ground truth. Research prefer this approach because it is quantitative, repeatable, and support multi-temporal analysis. Supervised classification is essential across many fields. When we talk about agriculture, we can talk about crop mapping. In hydrology, we can water body detection. At a geomorphological study, we can make an erosion modeling or monitoring expansion in the urban studies. Many advanced environmental analyses, like revised universal soil loss equation, specifically the factor C or land cover change detection, depends directly on it. Its strengths include high accuracy, strong control over class definitions, and the ability to incorporate field data. And its limitations are the need for good training samples, sensitivity to sampling bias, and labor intensity, especially in a complex landscape. The supervised classification workflow is straightforward. First, we collect training samples, representative patch of each type. Second, the system computes their spectral signatures, including reflectance, statistical, and separability. Third, we choose an algorithm, maybe a random forest or a maximum likelihood, with modern studies showing a clear advantage for a random forest. Then we run the classification, assigning each pixel to the most probable class. After that, we perform accuracy assessment. Maybe we can apply confusion matrix or overall accuracy or kappa. Finally, we refine the map with filtering, generalization, and manual correction to produce a clear result. Up to now, we have focused on supervised classification, which is very effective at the pixel level when we have good training data. However, as we move to high-resolution imagery or a landscape with complex or heterogeneous features, the pixel-based approach starts to show limitations. Shadows, edges, and a mixed pixel reduce accuracy. Here, object-based image analysis becomes useful. It improves on pixel-based classification too, but by grouping into meaningful objects rather than treating each pixel independently. This approach is particularly essential for high-resolution imagery, where a single land cover type may be represented by multiple pixels values due to shadows, edges, or within a class variability. OBIA integrates spectral, spatial, texture, or contextual features which help reduce misclassification errors that are common in pixel-based methods. The famous application, we can talk about building footprint extraction or agriculture field boundary map. We can mapping small water bodies, or we can detect tree crown. Segmentation, which is the core of object-based image analysis. What's the meaning of segmentation? Segmentation divides an image into objects, which are then analyzed as units rather as individual pixels. This step is central to OBIA because it defines the spatial units that classification will operate on. The key parameters we can talk about first, the scale. Small scales capture fine urban details, while large scales are suitable for forest or broad landscape features. We can talk about shape with color weighting. The color information dominates in natural landscapes, whereas shape is information is more important is a structure or built-up areas. The compactness and smoothness, this determines whether objects have tight or compact boundaries or elongated, maybe smooth shapes. Good segmentation reduced mixed pixel errors and enhance the use of texture and contextual information, improving overall classification accuracy. OBIA workflow steps first begins with segmentation, as I mentioned, which here we can define object using appropriate scale, shape, and compactance parameters. Then we can move to feature extraction, derive spectral, spatial, and textural, and contextual attributes from each object. Then we can move for training, where we can select a representative object for each class. And a classification will applied by, maybe we can use a random forest or rule-based approach to classify objects. Then the accuracy assessment evaluate results using an object-based confusion matrix. The benefits of OBIA that it reduces noise and mixed pixels errors, capture real-world object rather than isolated pixels, and incorporates a geometric, spatial, and contextual information. It also performs superiorly for high-resolution imagery and complex landscape. Now we move to the final and most advanced stage of classification, which is the deep learning. What makes deep learning different is that it doesn't rely on manually selecting spectral or spatial features. Instead, the model learns these features automatically, just as a human recognizes shapes, texture, and patterns when looking at an image. Deep learning looks at the image holistically. It analyzes both the spectral values and the spatial context, which allows it to distinguish subtle texture, complex structure, and mixed pixels that traditional classifiers struggles with. The capability make it especially accurate in heterogeneous or fragmented landscape where boundaries are irregular and classes overlap. In terms of performance, deep learning excels at detecting objects such as building roads or tree crowns, even when the environmental is complex or noisy. And several architectures are commonly used in remote sensing in this
دكتورة زينب عملت الكوهوت.
مش الحال. بس شوفي لي حنين الشير إذا حيمشي حالة بليز.
You are on زينب.
مش الحال بس بعد أنا ما فتت.
على الهوم بالهوم هي
وين؟
على اليمين
عليك وين؟ أوكي شفت. أوكي. مشي حال الشير سكرين.
يلا نصحى.
مفروض إنه إيه. يلا
مش الحال.
تمام. أوكي. We talked about now we can step to the workflow and key consideration for deep learning and remote sensing. First, inputs include okay. Inputs include the image tiles we want to analyze, labeled training data that defines the classes and optional indices like NDVI or maybe DEM to enhance feature detection. Next, the model stage involves training deep learning architecture. This could be maybe CNN or UNet or other suitable network, depending on the application. The outputs vary by task. Semantic segmentation provide pixel level labeling, while intense segmentation identifies objects individually, as with mask RCNN. Deep learning requires computational resources, including large data sets or sufficient training time and data to improve performance. Typically, use cases include high-resolution imagery, urban mapping, precious agriculture, and environmental monitoring, essentially any scenario where fine detail matters. The key takeaway is that deep learning doesn't replace supervised classification or OBIA. It complements them. When sufficient data and computational resource are available, it delivers the high accuracy for complex, heterogeneous landscape. By a brief comparison between the pixel-based or object-based or deep learning, pixel-based classification treats each pixel independently, so it works well when classes have clear spectral separations, but struggles with noise and limitation spatial context. OBIA improves OBIA improves the situation by grouping pixels into meaningful objects, enabling the use of shape, texture, or context, particularly effective in high-resolution imagery. While when we talk about deep learning, it goes further by learning scale spatial features automatically. It offers the highest accuracy in complex environments and automatic feature extraction. But it requires always a large training data sets and specialized computation. Each method has a different strengths, and selection depends on resolution, study area complexity, and available of the resources. As we can see, these four methods represent a progression from exploratory to advanced analytical techniques. The unsupervised discovers patterns, while a supervised integrates field knowledge, and object-based image analysis captures objects and context, while deep learning combines spectral, spatial, and contextual information for maximum accuracy. Together, they provide a comprehensive toolkit for remote sensing classification, adaptable to any landscape, and dataset resolution. Choosing the right classification method always when we want to select a classification method begins with the image resolution. If it is medium to large, medium resolution data tends to favor pixel-based methods, while high-resolution imagery benefits from OBIA or deep learning. If we take the landscape of complexity as another driver, homogeneous features or simple agriculture area can be mapped with a pixel-based approach, whereas urban mosaics, heterogeneous features require more advanced method. When we take the data availability, it is also matter. Under the samples limitation, pixels-based and object-based image analysis can be used, while deep learning excels when substantial labeled data and computing power are available. If interoperability is important, object-based image analysis offers transparent rules, and if accuracy are the priority, deep learning is typically the strongest option. Automation for local projects can be done by pixel-based or OBIA, but deep learning can be used for regional automation. Now, once a classification is complete, it is essential to evaluate its reliability. Accuracy assessment involves using metrics such as overall accuracy, kappa coefficient, and confusion matrices to identify errors or misclassified areas. The quality assurance ensures that the map is scientifically robust and ready for further analysis. Without this step, any subsequent modeling or decision-making could be compromised. Now we come to the final step, which is about integrating our classification outputs into a practical analysis. In the lower Litani Basin, water scarcity is a major challenge affecting sustainable irrigation. Our goal as scientists or researchers is to identifying optimal sites for rainwater harvesting ponds using the maps we generated from advanced classification techniques. The process involves weighted overlay sustainability modeling. Here, we combine multiple thematic layers: land cover with a slope map and a soil map and hydrology, and assign ways based on suitability criteria such as proximity maybe to water, soil type, and slope. The result is a suitability map that highlights the most appropriate locations for ponds, supports agriculture planning by identifying area suitable for cultivation, and helps prioritize zones for sustainable water management. Thus, the key takeaway is that our classification outputs are not just a map. They are actionable spatial data that directly inform evidence-based environmental and resource decisions. This demonstrates how remote sensing and GIS connect analytical techniques to real-world problems. اوكي
ما تعملش
لا سلايدات بس. We are now moving from theory to practice, applying our knowledge to the Lower Litani Basin case study. Our objective is applying advanced random forest classification and integrates outputs into a spatial suitability modeling for evidence-based decision-making. Our study area is a Lower Litani Basin, identifying optimal sites for rainwater harvesting infrastructure. The methodology is about a two-part approach: advanced image classification, followed by weighted overlay sustainability suitability analysis. The first part, the data quality assurance, first, after opening the ArcGIS Pro, load the corrected satellite image. This is the solid foundation which we built up on the last session. The first step is always data quality assurance. Please ensure you have loaded your radiometrically and atmospherically corrected image, or maybe you can download it L2A for Sentinel-2. Remember that the crucial note, uncorrected data will lead to inaccurate spectral signatures. We reach the training sample manager by opening the training sample manager by going to the imagery tab, select classification tools, and open the training sample manager. We need to collect samples of our 5 key classes, which are water, dense vegetation, spare vegetation, and built-up areas, and the critical classes for our case bare soil. As you collect your samples, always remember the practice for training sample. Use the drawing mode to create multiple small homogeneous polygons per each class to capture spectral variability accuracy. The quality of your training data directly determines the quality of your final map. Here, as you collect your samples, use the drawing mode as this we can mention. Now, the critical quality checkup, especially the spectral separability analysis. We can click to evaluate training samples in the manager. Before we train any model, we must perform the spectral separability check. This is to a quality check step. We can do it by the evaluate training samples. Focus on the transformed divergence TD values. The TD rule states that the value between any two classes should ideally be greater than or equal 1,900 for excellent separability. If you see a value below 1,700, that is a red flag. It means those two classes are spectrally confused. You must either collect purer samples or merge the overlapping classes before proceeding. This step ensures the model is trained on a distinct spectral signature, improving the final accuracy. Now we can turn the next step, which is training the random forest classifier. Open the Train Random Trees classifier tool. Now that we have validated our training data, let's train our advanced classifier. You can reach or go the analysis, then tools, and reach the Train Random Trees classifier. Set the input raster to your corrected image and the input training sample file to your validated. For a number of trees, the default one is 500, is a robust choice. Remember that a random forest is a simple learning method, high resistance for overfitting. Run the tool and wait the classifier to definition. Now applying the classifier to produce a land cover map. We apply the model to the entire image, search for the classify raster rule tool. The inputs are simple, your original image and the classifier definition file we just created. Save the output as land cover for Litani. The output is our thematic raster. It is the crucial first input of our decision-making process, as noted in the guide that I will send it. The second part, we move to suitability modeling or the weighted overlay. Here, we can make the reclassifying the land cover map or the suitability scale. We can open the reclassify tool. We now transition from classification to suitability modeling, where our goal is to find the best sites for rainwater harvesting ponds. This requires converting our categorical land cover map into a suitability scale. Go to the reclassify tool. The input is our land cover for Litani. We will assign values from 1, the least suitable, to 5, the most suitable, based on the suitability criteria. We can see the table which mentioned in the guide. Assign bare soil a value of 5 because it is highly suitable. Low constructions cost and high runoff potential. Conversely, built-up areas and water get a number 1. Demonstrate setting the reclassification table and save as land cover reclass. Now we can briefly mention the slope and proximity steps, which, as outlined, you would now prepare your other criteria for such research. Here, for our example, we must talk about slope, which derived from digital elevation model, and proximity to roads, which derived using the Euclidean distance. You must reclassify both of these to the same 1 to 5 suitability scale. For example, moderate scale, which is between 5 and 15 degrees, receive the highest value, which is number 5, for optimal runoff and stability. Here we reach the final decision, which is the weighted overlay. Open the weighted overlay tool. This is the final step, the decision tool. Search for the weighted overlay tool. This allows us to combine our criteria based on their relative importance. Add your 3 or maybe 4 reclassified layer if we talk about a land cover, slope, or proximity to road, or maybe also hydrology. Now we assign the weights. These weights reflect the expert input on the importance of each factor for our case study. We assign, for example, if we take only 3 criteria, land cover is about 40%, which is the most important criteria. Slope maybe 30%. Here the numbers is 50, 30, and 20 for road proximity. Set the weights in the tool and run the tool. The output suitability TIFF is your final suitability map. The highest pixel values on this map represent the optimal sites for constructing the rainwater harvesting ponds. We have successfully transformed a complex satellite image into a direct evidence-based recommendation for water source management. Must mentioned as the important note, the weights and suitability values presented are initial assumptions. They must be reviewed and adjusted in consultation with a hydrologist or agricultural engineer before implementation. Critical consideration, we can mention about data quality is paramount, expert validation required, and random forest advanced. This is the final slide for our today's session. Here we can move from remote sensing image to a specific decision make analysis. Now I will end our meeting. Haneen wala doctor, and we will meet again the next week inshallah.